Okay, so we just did, okay, a bunch of algebra and calculus, is we had our simple harmonic oscillator, okay, we used Newton's second law, F equals ma, and we found that that's the position as a function of time, okay? Remember, we can't use that, right? That's only when the acceleration is constant. This thing does not have constant acceleration. Speeds up, slows down, speeds up, slows down, speeds up, slows down. Okay, so acceleration is not constant. So this is the position as a function of time, all right? But when I write this, okay, when we write that, we have to include, well, what is this omega? Omega was the square root of k over m. That just came from the algebra from the previous section, okay? Well, omega is square root of k over m, but with the period, okay, the period is 2 pi over omega. So the period is 2 pi divided by that. Okay, so if I put that in the denominator, okay, put square root of k over m and square root of k over m in the denominator, then that flips up and I wind up in the expression like that. Okay, so the period, okay, is 2 pi times the square root of m over k. Okay, so m is the mass of the block and k is the spring constant, right? So we'll be doing a lab in which you'll have an oscillating system. Okay, you know the mass of the block, you know the spring constant, okay, and you calculate the period, and you compare that to the measured period while that thing is oscillating up and down in front of you. And we'll see as it turns out that this expression is for an ideal case where the spring's mass is negligible compared to the oscillating mass, okay? And in lab, we'll see that the spring itself, okay, for some of the masses we have attached, the spring itself is sometimes 3 times heavier, okay, or 3 times more mass than the block, okay? And then we'll see in lab that you actually will have to include a portion, some constant times the spring mass, okay? But don't worry about that. We'll do that in lab, okay? All right. Okay, now the good news in this chapter is if you know the period, okay, you instantly know the frequency, okay, because the frequency is 1 over the period. So I invert the period to get the frequency, okay? And this was another property of simple harmonic motion, okay? And that property is if you have a system and you find that the frequency and the period are independent of a particular quantity. Okay, now let's look back here. So we started with this picture. Okay, someone pulls this thing back and they let it go. Okay, and I want to look at the period here. Okay, because anything I can say about the period goes for the frequency in the sense that it's just one's the inverse of the other. Okay, so I look at what does the period depend on. So I took the mass off the shelf, took a spring off the shelf, and I oscillated it. Okay, well, what quantity, what parameter up here would you expect to show up down here, okay, over here, that isn't there, all right? So the original geometry of the problem here, there's another parameter that you might think would show up here, okay? Maybe the amplitude, okay? Yeah, the amplitude doesn't show up in the expression for the period, all right? And that's not obvious that that would happen, all right? So we find that the frequency, okay, whoops, there's a C right there. We'll fix that. Here, I'll put a C right there. Frequency, okay? The frequency and the period are independent, okay, independent of the amplitude, okay? And if you have a system where you bring this thing back, okay, so here's the person that they brought it back and they let it go and it goes back and forth. 1, 2, 3, 4, okay? Now, what if they bring it way back here, okay, and they let it go, okay? It's going to go much further distance, but it's going to be moving faster, and it's going to move like this: 1, 2, 3, 4. Okay, the period's going to be the exact same thing. Okay, so I'm going to show you a video of where I have an oscillating system. Okay, and at one point the amplitude is small, oscillates back and forth, and you can measure the period. And then they do it where the amplitude is large, oscillates back and forth, and you can see that the period is the exact same.
1, 2, 3, 10. 1, 2, 3, 9, 10.
Okay, and now actually, now that you have this expression, okay, for the period, all right, if I square both sides, so if I square both sides, I have a t squared, 4 pi squared, m over k. And if I solve this for m, okay, solve that for m, right, this is another way to measure mass. Okay, so we've measured mass many different ways this semester. Put on the scale, okay, you measure its gravitational mass. We've accelerated it with known forces. We measure its inertial mass. We accelerated it in a circle. We measured its resistance to move in a circle, its inertial mass. Then we rotated it, I think in the last lab, on axis and then off axis, okay? We measured mass that way. Here's another way to measure mass, okay? You can oscillate it back and forth, okay? You can measure the period, you know, the spring constant of the spring, and you can measure mass that way. Okay, essentially, you're still measuring its resistance to move back and forth, okay? But it's another way to measure mass. You can oscillate it, all right? So what is this person's profession? Okay, they're an astronaut. Okay, so an astronaut's up in the space station, all right? They're going to sit up there for a couple months and maybe mission control in Houston, all right? They want to monitor their body mass, all right? So if they're standing on a scale, what does the scale read? It reads 0, okay, because everything's falling, okay? They're in a weightless environment. So they sit in the chair, all right, and they can oscillate back and forth like that, okay? And then watching the live feed, okay, they can measure the period, okay? How do you find the spring constant? Well, you can do that before you launch this thing up in the air, and then you can monitor and measure that person's mass. Now, another thing that we kind of skipped over a little bit, okay, well, didn't talk about much, is I've been going in between drawing those type of pictures and maybe a mass oscillating up and down where I showed you a demo of that, and they look like two totally different geometries, okay? So it's not very obvious that if I have this system here, okay, and it's oscillating, has a certain frequency, okay, and a certain period. If I now take the same mass and the same spring, okay, and hang it vertically, okay, it turns out that you have the exact same frequency and the exact same period, all right? So that's not obvious that happens. I think I have a proof posted somewhere. If you go into somewhere in files on the Wiley site and look in lecture notes, I think there's a mass spring proof, okay? So because the main thing that's different is this thing's oscillating back and forth. You have the normal force, okay? You have mg, all right? Now you have the spring force, obviously, okay, in that direction, depending which way it's going, you have the spring force. But in this picture, okay, you have mg in the direction that it's oscillating. So that's totally different geometry. Okay, you would think that mg would affect the period or the frequency, okay? But all that it does, okay, so if here's your spring, this is your relaxed spring position, y equals 0, okay, and you put a mass right here, okay, and you lower it slowly with your hand, okay, don't drop it, and then you just slowly let go and take your hand away, okay, that mass will just sit right there. So all the effect that mg did is it just shifted the equilibrium position from up here to down there, okay? So it just has a new equilibrium position. Remember, equilibrium means net force equals 0, okay? How do we know the net force is 0 here? Well, acceleration is 0, it's not moving, okay? So all that mg does, it shifts the equilibrium position, okay? It's not very obvious that it doesn't affect the period and frequency, and it doesn't. So the frequency remains the same, even though it's going up and down vertically. So these two systems act exactly the same way.